There is a machine buried 60 meters beneath the streets of Kuala Lumpur right now. It is longer than a Boeing 747. It weighs 4,300 tons, and it is cutting through solid rock at a rate that, 10 years ago, would have required twice the equipment and 3 times the time. The city above it has no idea it's there. Traffic moves, markets open, children go to school, and 60 meters below all of it, something the size of an apartment block is eating through the earth at the pace of a slow walk, lining the tunnel behind it with concrete rings as it goes, leaving a finished underground corridor in its wake. That machine was designed in China. It was built in China, and the team operating it is Chinese. Now here's the part that changes the story. In 2008, China did not manufacture a single large-diameter tunnel boring machine. Not one. Every TBM digging beneath a Chinese city had to be imported, from Germany, from Japan, from the United States, at a cost of up to $150 million per unit, with lead times of 2 to 3 years, and with foreign engineers who controlled the maintenance contracts and decided when parts got shipped and when they didn't. Today, China manufactures 70% of all tunnel boring machines sold on Earth. Not 20%, not 40%, 70%. And in the last 3 years, Chinese TBMs have been contracted for major infrastructure projects in 56 countries across 6 continents. This is not a manufacturing story. This is a story about how one country looked at the most complex machine in construction, decided it was too important to keep buying from someone else, and then spent 15 years learning to build it better than anyone who came before. Before we get into what China built, you need to understand what a tunnel boring machine actually is. Because most people have a completely wrong idea. It is not a drill. Stand at the entrance to an active TBM project, and what you are looking at is not a piece of equipment. It is an underground city, moving forward in slow motion. At the very front, a rotating cutter head, anywhere from 6 to 17 meters across, presses against the rock face with up to 100,000 kilonewtons of force. To translate that number into something a human can feel, that is the equivalent of taking 30 fully loaded Airbus A380s, stacking them nose to tail above a single point, and pushing straight down. The cutter head chews the rock into fragments. Behind it, a conveyor system pulls the debris backward through the machine, hundreds of tons per hour, moving continuously. Behind that, a ring-building system picks up precast concrete segments and installs them against the tunnel wall, one ring every 30 to 90 minutes, permanently lining the tunnel as the machine advances. Behind that, ventilation ducts, high-voltage power cables, pressurized water supply, worker rest areas, control rooms, laser guidance systems, and real-time geological monitoring equipment. All of it mounted on a trailing gantry that can stretch back 150 meters. Everything moves forward together. The whole system breathes as one machine. And it does all of this at a speed that, from above ground, you could not perceive. On a good day in favorable geology, a large TBM advances 20 to 30 meters. That is the length of 2 city buses per day. The Gotthard Base Tunnel in Switzerland, 57 kilometers, the longest railway tunnel in the world, took 17 years to complete. The machines never stopped. They just moved very, very slowly. This is why TBMs matter beyond the engineering spectacle. Underground infrastructure has no shortcut. You cannot pour concrete around a mountain. You cannot build a bridge under a city. The only way through is through, and the machine that does the going determines how long it takes, how much it costs, and whether the project happens at all. The global demand for that kind of infrastructure is accelerating faster than at any point in the last century. Every major city on Earth is running out of surface space. Rail, water tunnels, power conduits, highway bypasses, all of it is going underground. The International Tunneling Association projects that global tunnel construction spending will exceed $800 billion by 2030. Every single one of those projects needs a TBM. Whoever controls the supply of TBMs controls the pace at which the modern world can build underground. For most of the 20th century, that control sat with Herrenknecht in Germany and Robbins in the United States. They set the price. They set the delivery schedule. They set the service terms. If you needed a machine and you needed it to work, you bought from them, you waited for them, and you paid what they asked. That era is ending. The man who did more than anyone else to end it was not an engineer. His name is Tan Xunhui. In the 1990s, he was running a construction machinery company in Changsha, the kind of company that made cranes and excavators and the ordinary equipment of building. He had no background in tunneling. He had no background in precision manufacturing. What he had was a problem that he could not stop thinking about. China was building subways, dozens of cities, simultaneously, racing to put rail underground before their streets became permanently gridlocked. And every time a new subway contract was awarded, the same thing happened. The project team called Germany or Japan, placed an order for a TBM, and then waited. Waited 2 years for delivery. Waited 6 weeks when a bearing failed and the replacement had to be flown in from overseas. Waited while the foreign service engineers arrived on their own schedule, fixed what they chose to fix, and left. Tan Xunhui watched one project in Shenzhen sit idle for 11 weeks because a single hydraulic component failed and the manufacturer's nearest available engineer was in Singapore. 11 weeks, on a subway line that had already been under construction for 2 years. He decided the dependency itself was the problem, not the machine. In 2009, 1 year after Craig completed its first domestic TBM, Tan founded a company that would later become CRCHI, China Railway Construction Heavy Industry. His approach was different from CREG's, where CREG came from the state railway system and had access to government engineering institutes. Tan's team was smaller, faster, and structured around a single question. Not, how do we build a TBM, but what does the person operating this machine actually need it to do? The first machine his team produced failed its initial ground test in 2011. The cutter head torque was insufficient for the rock hardness in the test tunnel. They stripped the machine, rebuilt the drive system, and ran the test again. It passed on the second attempt, 3 months later. By 2014, CRCHI had delivered machines to 7 subway projects. By 2017, it had become the second largest TBM manufacturer in China. By 2022, it was exporting to Southeast Asia, the Middle East, and Eastern Europe. Tan has said in interviews that the 11 weeks in Shenzhen never left him. That every machine his company delivers is, in some sense, an answer to that 11-week silence. In 2008, when Craig completed the Chinajan No. 1, the first domestically designed large-diameter TBM to enter service, the reaction from the German industry was measured. Polite, but measured. The machine worked. That was undeniable. But the cutter head life was shorter than a Herrenknecht equivalent. The disc cutters, the actual rock-cutting elements, tungsten carbide wheels that press into the rock face and must be replaced after a certain number of hours, wore out faster. The hydraulic thrust system required more maintenance, and the control software, by the standards of what Herrenknecht was shipping at the time, was limited. None of this was surprising. First-generation domestic production in any category is rarely world-class from day one. What mattered was not where the machines started. What mattered was the rate at which they improved. Between 2008 and 2015, Chinese TBM engineers had access to something that no Western manufacturer had ever had at the same scale: an enormous and simultaneous real-world test environment. 40 cities building subways at once, hundreds of tunnel bores progressing in parallel, every machine generating operational data, vibration frequencies, cutter wear rates, thrust pressure curves, geological response patterns, that fed back into the next design cycle. Herrenknecht, in the same period, was delivering perhaps 80 to 100 machines per year globally. CREG and CRCHI together were delivering more than that into Chinese projects alone. The learning curve that typically takes a Western manufacturer a decade compressed into 3 years. By 2015, Craig had filed more TBM-related patents than any other company in the world, surpassing Herrenknecht, surpassing Robbins, surpassing the combined output of every European competitor. That number requires a moment. Patent filings are not proof of innovation quality, but they are a leading indicator of engineering activity and institutional knowledge accumulation. The volume of patent output tells you how many engineers are actively solving problems at the frontier of a technology. By 2015, more of those engineers were Chinese than German, American, and Japanese combined. By 2018, a Craig machine completed the Wuhan Yangtze River Tunnel expansion, 11.6 kilometers, dual bore, through unconsolidated riverbed sediment that is among the most geologically punishing material a TBM can encounter. Sediment that shifts under pressure. Sediment that can flow into the face of the machine if the pressure balance fails. Sediment that gives the cutters nothing solid to push against, and instead tries to swallow the entire front of the machine. The project finished ahead of schedule. Herrenknecht's response, in a 2019 industry report, was carefully worded. They described Chinese machines as competitive in specific segments. What they meant was, we can no longer compete on price in 60% of global contracts. The argument that Chinese TBMs simply undercut European machines on price is the wrong argument. It was true in 2012. It is no longer the full story. In 2021, Craig delivered a machine for a project beneath the Tian Shan mountain range in Xinjiang, drilling through granite, quartzite, and fractured fault zones at altitudes where air pressure drops and hydraulic systems behave differently than they do at sea level. This is not favorable tunneling terrain. The rock is hard enough to destroy a standard disc cutter in hours. The fault zones are unpredictable. You can be drilling through competent granite, and then, with no surface warning, hit a fracture zone where the rock is loose, wet, and under tectonic stress. The machine built for this project incorporated something that had not existed in production TBMs before, a real-time acoustic monitoring system. 240 sensors distributed across the cutter head and the face of the machine, continuously analyzing the sound signature of the rock being cut. Not radar, not sonar. Acoustic resonance, the specific frequencies that different rock types and different rock conditions produce when a tungsten carbide disc presses against them at 6 revolutions per minute. The onboard system, trained on operational data from 34 previous projects, could detect a geological transition 8 to 12 meters ahead of the cutting face. Before the machine reached the change, before the operators could see it in their core samples, when it detected a transition from hard granite to fractured fault zone, the kind of transition that, if met with unchanged thrust settings, would cause a cutter head bearing failure within 18 hours, it automatically adjusted thrust force, cutter rotation speed, and face support pressure. The human operators received a notification that the system had intervened. They did not have to do anything. Compare that to the Niagara Tunnel project in Canada in 2011. A Robbins TBM, the most experienced American manufacturer in the world, encountered unexpected fractured rock that the Geological Survey had not identified. The operators did not detect the transition in time. The cutter head bearing failed catastrophically. The repair and delay cost $800 million and added 3 years to the project timeline. The Tian Shan machine encountered conditions of equivalent severity 47 times during its project. The acoustic system engaged each time. The machine completed the tunnel without a single unplanned stoppage. Then there is the size. In 2023, Craig completed the manufacturing of a TBM with a cutter head diameter of 16.07 meters, the largest ever built. If you stood that cutter head on its edge in a city street, it would be taller than a 5-story building. At full thrust, it generates force equivalent to 2,600 fully loaded freight cars, pushing simultaneously against a single surface. It was built for the Shenzhen-Zhongshan Cross-Sea Tunnel Link, a project crossing the Pearl River estuary at 40 meters below the seabed, in conditions that include soft marine sediment, high water pressure, and the constant low-frequency vibration of one of the world's busiest shipping channels overhead. No equivalent machine exists anywhere else in the world. Not in Germany, not in Japan, not in the United States. If you need a tunnel of that diameter dug anywhere on Earth, there is one country you call. China's TBM dominance became visible to the rest of the world, the way most industrial shifts become visible. Not in a single announcement, but in a sequence of contracts that individually seem unremarkable and collectively represent something that cannot be reversed. The Riyadh Metro, the largest metro construction project in the Middle East when it was commissioned. CREG machines. The Frankfurt Stadtbahn expansion, a German city, expanding its underground rail system using Chinese equipment. 4 machines, 2 from CREG directly, 2 from a subsidiary operating under a European partnership structure, because the procurement rules required a European entity on the contract. Lima Metro Line 2 in Peru, originally awarded to a Herrenknecht consortium. A section was retendered in 2019 after cost overruns. Craig won. On price. On delivery schedule. Both. And then, in 2024, a Craig machine began drilling beneath the Swiss Alps, Switzerland, the country where modern tunnel engineering was essentially invented, where the Gotthard Base Tunnel stands as the defining achievement of 21st century civil engineering, where Herrenknecht has operated for decades as something close to a national industrial institution. A Chinese TBM, operating in Switzerland, on a railway project that Swiss engineers designed and Swiss contractors are building. The project manager, speaking to an industry publication, said the machine was technically competitive in every specification that mattered for the application. He noted that the delivery timeline, 14 months from contract signature to machine on site, was not achievable through any of the manufacturers they had previously worked with. 14 months. The comparable figure for a Herrenknecht machine of equivalent specification, 24 to 36 months. The gap is not primarily technological. Herrenknecht could almost certainly design a machine with equivalent or superior acoustic monitoring, equivalent bearing systems, equivalent cutter head geometry. The engineering knowledge exists. What does not exist and cannot be quickly created is the supply chain. A Chinese TBM is manufactured inside an industrial ecosystem where the structural steel comes from a domestic mill 200 kilometers away, the hydraulic components from a supplier cluster in Hunan, the control electronics from Shenzhen, the bearings from a specialist facility that also supplies the high-speed rail program and the aerospace sector. When a component needs to be changed mid-project, the replacement is on a truck within 48 hours. Herrenknecht sources critical components from suppliers across Germany, Austria, Sweden, and Japan. Each one is excellent. Each one is also a dependency, a node in a supply chain that crosses borders, navigates customs regimes, and operates on its own schedule. The Chinese domestic TBM supply chain has been built over 15 years as a deliberate industrial policy outcome, not as a byproduct of a single company's procurement decisions. It cannot be replicated by a Western manufacturer deciding next year to start competing again. The infrastructure that supports it is not for sale. Herrenknecht remains the most technically sophisticated TBM manufacturer in the world for the hardest projects. Nobody disputes this. For the deepest mines, the most geologically chaotic conditions, the projects where the wrong answer costs $1 billion and several years, German engineering still sets the ceiling. But those projects are a thin slice of global demand. Most tunnel projects are not the English Channel or Gotthard. Most are urban rail extensions in cities that have been waiting 15 years for the budget to arrive. Water tunnels connecting reservoirs to growing populations. Highway bypasses through hills that were always too expensive to tunnel before. Projects where the geology is surveyed and understood, the specification is standard, and the constraint is not engineering complexity, but cost and schedule. That market, the volume market, the market that pays for the industry, belongs to China now. Robbins, the American manufacturer that dug some of the defining tunnels of the 20th century, has been in contraction for years. In 2022, the company restructured towards servicing and refurbishing existing machines rather than new manufacturing. The pipeline of new orders that would justify a different strategy is not there. Japan's manufacturers, long valued for their precision and their ability to operate in the dense, earthquake-prone urban geology of Asian cities, have found no answer to Chinese pricing that their corporate cost structures can absorb. They remain competitive in the Japanese domestic market. Beyond it, their share is declining. The competitive gap is not closing. In 2015, a comparable specification Chinese TBM cost roughly 25% less than a German equivalent. By 2023, that gap had widened to 35 to 40%. Not because Chinese quality declined, because Chinese production volume increased, domestic supply chains matured, and manufacturing efficiency compounded year over year. The machines improved while the price fell. More volume means more operational data. More data means better design. Better design wins more contracts. More contracts means more volume. The cycle that built Chinese dominance in solar panels, in lithium batteries, in electric vehicles, the same cycle, running at the same logic, now running in tunnel boring machines. In 2008, China spent $12 billion buying tunnel boring machines from the rest of the world. Today, the rest of the world buys its tunnel boring machines from China. That transition, from the most dependent importer to the dominant global supplier, in the most mechanically complex category of construction equipment that exists, happened in 15 years. 15 years is not a geological timescale. It is not even a career. It is the span between the first iPhone and now, between the 2008 financial crisis and the first COVID lockdowns. Long enough that the change happened gradually enough not to make headlines, short enough that the engineers who watched it begin can still describe what the starting point felt like. The underground infrastructure that will shape how the next generation of cities move people, distribute water and route power is being dug right now. In Kuala Lumpur, in Riyadh, in Lima, in Frankfurt, in the Swiss Alps. The decisions about which machines do that digging, and who made them, and on whose terms, were made years ago, in factories and engineering institutes and procurement offices that most of the world was not paying attention to. The tunnels are already being bored. The question is not whether this happened. The question is which industry you look at next, and whether you see the same pattern before it finishes running. If this opens something you hadn't considered before, the like button is the fastest signal you can send. And if there is a sector where you think the same cycle is already underway, write it in the comments. We read every one.